Hello, we're going to look at some fluid dynamics concepts today. The first one we're looking at is continuity. And here's a nice diagram that illustrates what we're talking about. So if this is a nozzle, maybe we can envision like a hose over here connected to it, and we have water flowing through. We're going to use water because that's a pretty relatable thing for everybody to think about. And we know water is incompressible. Okay, so if we have water flowing in on this side, and this nozzle is already full of water, and we pump in a certain amount of water in a certain amount of time here, during that same time period, that amount of water must be pushed out this side also, okay? So whatever we push in here must be pushed out the other side. So we're gonna talk about that. So that's really a conservation of mass idea. We're not gonna be creating more mass in this space by pushing water in. It's just gonna, whatever we push in is gonna be pushed out also. I'm gonna use capital V for volume, and I'm gonna use lowercase v for speed. So the volume in, the volumetric flow rate in must be equal to the volumetric flow rate out. And I'm gonna try to convince you that this is an equivalent expression. The cross-sectional area at position 1 of this fluid flow times the velocity there is going to be equal to the cross-sectional area at position 2 times the velocity there. And that this combination is actually volumetric flow rate at position 1, and this combination is actually volumetric flow rate at position 2. So let's just play around with that idea for a little bit. Volumetric flow rate. So how would I have not very much flow through this nozzle? Well, I could have a small cross-sectional area and not very much speed right there. So that wouldn't be very much water going through that section. Well, how could I have a large volumetric flow rate? Well, I could have a huge cross-sectional area and such a high speed of the flow of the water right there. That would be a lot of volume per second going through there if I had a big cross-sectional area and lots of speed. So hopefully that convinces you that these are equivalent. I'm just going to go ahead and go a little bit further on that, trying to convince you. So what are the units of these things? So this is meters cubed per second, volume per second. And let's go over here and look at what we have over here. So cross-sectional area would be meters squared. And then speed is meters per second. And so what do you get when you multiply those things together? Meters cubed, or volume per second. And so that's why those things are equivalent. So this has a pretty good insight on what's going to happen here. If you have a garden hose and you want to spray your brother or sister with it, what do? You don't just take the garden hose, grab it, and just point at them and the water like leaks out. You put your thumb over the end of the hose and you make a nozzle, and that forces the water to whoosh, squirt out extra fast out the end. And so if we have, for this situation, we know we have a large cross-sectional area at position 1, and we know we have a small cross-sectional area at position 2, then we know that if we want this volumetric flow rate to be the same, we must have have an increased speed of that water at position 2 and a lower speed at position 1 to make those two sides equal. And so there's your continuity equation explained for you. Now, one kind of sneaky place this happens that kind of blows my mind is if you take any container of water and you dump it out all of a sudden, like big enough that it's going to pour out for a little while, you're going to notice that when it first comes out, that water is going slow and there's a bigger cross-sectional stream there. I'm just talking about like dumping this out in air. And when that water falls, it's going to get going faster and faster compared to it's slowly going up here because you're just dumping it out up here, right? Gravity's going to pull and make it faster down here, and you'll notice that that stream of water always necks down to abide by the continuity equation. If it did not neck down, you would be creating matter. You'd have actually more matter at the bottom of the stream. You'd be like creating matter in the universe. So it has to neck down, which is kind of crazy to think about. All right, so there's continuity for you.